Good morning, students. Dear students, today we are going to learn the force on a charged particle in a uniform magnetic field. Rather, we will move further to consider the dynamics of the charged particle in it. That means we are going to find how the trajectory of the charged particle will be and how its velocity will change when the force is applied on it. And find the conditions on the chart, find the conditions where the charged particle will not experience the force, even it will not be deflected by the magnetic field. Okay. So let us move to that part. So for that case, we have considered a vertically inward magnetic field here, and that is uniform. We know the vertically inward magnetic field actually given or designated by the cross sign. That means the magnetic field is pointing away from you. I have chosen the axis. So in this direction, it is x-axis, the right side. The upward side is y-axis, and the z-axis, according to the right-handed coordinate system, is pointing towards you. Okay, it is, and the magnetic field is now pointing opposite to the z-axis because it is taken vertically inward. So magnetic field can be written as its magnitude into the its kinetic unit vector, right? But k cap is the unit vector along positive z-axis. I should write v into minus k cap because it is pointing inward, right? So now we are considering a charged particle here entering in this magnetic field. So I am considering the case number one. There are two cases. One, when the charged particle entering enters perpendicular to B magnetic field. That means it is entering in XY plane. Okay, because XY plane is the is perpendicular to the Z axis. Okay, that means initially it has so the velocity is taken u, and after experiencing the force, suppose the particle is moving in this direction, and now the velocity, it is the one velocity at time t, it has two components. Rather, I have taken the three components here. I do not know, say, uh, that what are the components are zero or non-zero. So I have taken the three components. So I am now assuming the particle has the velocity, but it has three components when it will experience a force. So in this direction, that is one is Vx, another is Vy, and obviously in this the z direction, that is Vz. Okay. So Vy is taken along negative. Sorry, I have to write it properly. So that is it is in this direction Vx, it is Vy. And the V has taken due to since I have taken the V in this direction, so I have taken the Vx in negative x-axis. It does not matter. But the matter is we have considered the velocity. We have considered the velocity at at a particular moment in 3D. So now we are going to write the force. We know the force acting on the particle is given by the Lorentz force formula, and that is F equal to Q into V cross B, where the Q is the charge of uh, the particle. We have to remember that for this from this expression that the force, since it is the force is found from the cross product of the velocity and B and the magnetic field, the Ft at any moment is perpendicular to V and B. Okay, good. Okay, fantastic. So we have already, that is a very important fact. So the force is always perpendicular to the V and B. That means we have to consider the plane where the V and B are lying, and to the plane the F must be perpendicular according to the force law at any time. Okay. That is the first. Second is, second is the force. This force is non-conservative force. This is a property of the Lorentz force. Okay, so that is very important thing to have to remember. Which is a property of the. So let us move to the solution of the problem. We have to write the equation of motion, and and then we can get what are the velocities and which components are zero or non-zero according to this force law. So we have already seen that the force, since the force Q and V and B, then Q is Vx I cap. I'm dividing the V into three components. I'm decomposing the V in three components, Vy j cap and Vz k cap. So that is V, and I'm multiplying with B. And since has already been written in terms of the unit vector, that is V into minus k cap, so that is the final expression of the velocity. Now I'm taking the cross product with the usual rule. So Vx I cap cross minus k cap and Vy j cap cross minus k cap. Good. And k cap cross k cap is zero. We know this from the property of cross product because as any vector parallel or anti-parallel to that, the cross product between them is zero. Yeah. So I'm taking the minus sign outside common, so it becomes Vx I cap cross k cap and Vy j cap cross k cap. Good. So we know from class 11 that according to the cyclic rule, that means I, J, and K. So when I cross J, that is K. So if I move in this direction clockwise, then I will find all the cross product with positive sign in the result. In the sense that I will get I cross J is K, then I will move to the K again, J cross K is I, and like this, and K cross I is J. Is okay. So I have taken this from class 11. I think everybody knows this. And if I will move opposite, then the negative sign will appear because of the product of the cross product. So using that, so we have already seen the J cross K, which is present here, that is I cap. So I'm writing this. So that is Vy I cap. But the first term actually contains I cross K, and I cross K is opposite of K cross I, which is J cap. So it is minus J cap. So that is minus Vx J cap. So now I'm taking the minus sign from outside to inside. So it becomes QVx J cap minus Vy I cap. Got it. So we have found the force finally, and that will give me the all the characteristics of the motion. Good. So now I'm going to decompose the force itself. So Fx I cap, Fy j cap, and Fz k cap, and compare the both sides of the coefficients of j cap, I cap, and k cap. So if I compare the both sides, so we can write, so Fx equal to minus q Vy I cap. Sorry, there must be a B, right? So I missed the B at every line in magnetic field. Otherwise, there is no meaning of this calculation. So minus qvyb, and fy is qvxb, and fz equal to 0. So there are three equations, and we have to solve this equation. Okay. The most easiest equation is the third one. So I'm going to name and numerate this equation. So I have to number those equations. So the from third equation we can solve the problem very easily. The first, if z is 0, that means the acceleration on z-axis is 0. Acceleration of the z-axis is 0, so that means vz is constant. The velocity along z-axis is constant. But how can I find the constant itself? So it is telling that vz at any time is equal to constant. But we know from the initial condition, in the sense that initially when the particle is entering, it is entering in xy plane. That means from initial condition, so at t equal to 0, so vz 0 must be uz, and which is 0. That means the constant itself is 0. That means the conclusion is, so vz is 0 at any time of the motion. So conclusion is very important conclusion. So if the particle enters in xy plane and the magnetic field is perpendicular to it, it remains in xy plane because there are no velocity we have found along z-axis at any moment. Because that is a big conclusion we have drawn here. So next we move to the other equation. So other equation is telling the fx is minus qvby, sorry, qvvy, and fy is qvvx. These two equations can be solved with these two equations. If we will see that these two equation number 2 and 3, we can observe the equation for the velocity x vx involves vy, and equation of the vy involves vx. So I'm writing in differential form in the sense that I'm bringing the derivative. Um, I'm writing the fx as max, and mx can be written as dvx dt, that is minus qvy, and fy is minus my mdvy dt, that is qvvx. Okay, so you can easily now explicitly see that two equations. The equation of the Vx involves Vy, and equation of Vy involves Vx. So these two equations are called coupled equation. This type of equations are called coupled. So to decouple them, this is very easiest way to decouple them. Uh, so we have to multiply the equation 2 with Vx and equation 3 with Vy and add them up. Why I am doing so? Because the right hand side of these two equations become equal, right? So I'm writing now, that is m dvx dt vx plus m dvy dt vy equal to 0, because the right hand sides become equal, and in the both cases in the right hand side we have found the qb vy vx, right? So the final equation, so these are our on the second, what should I say? That is the equation before the final equation. So we know from the derivatives of Vx that if I write the Vx square, the derivative of the Vx square it can be written as Vx dVx dt with a factor 2 outside. So using this fact, I can write that Vx dVx dt can be written as d dt of half Vx square. Similarly, Vy dVy dt is d dt of half Vy square. Then if I apply them here, then this equation becomes DDT. Just I am skipping one line. I think a student can understand that it can be easily done. So I'm first taking m common and divided 0 by m, and it will give me the 0. So the equation becomes dvy dt vy 0. Then I have brought those here. So it becomes ddt of half vx square plus vy square is 0. But half is also constant. So again, it can be written as ddt of vx square plus vy square is equal to 0. That means the vx square plus vy square equal to constant. So this is the final expression. We can actually get this equation from the very next line of this equation. But since I have to show all the steps here. That's why I have brought all the steps. I have gone through all the steps properly. So this equation, so we have found the dynamics of this particle right now. So whenever the particle is entering in xy plane at any moment, so vx square plus vy square, the square of the components of the velocity is always constant. So this constant again using the initial value problem. So initial values, initial conditions. This constant must be same at any instant. So if I take the instant as xt equal to 0, so at t equal to 0, right? At t equal to 0, the vx is ux and vy is uy. So that is ux square plus vy square. And the ux square plus uy square is actually the sum of the square of the components. And which is that's why it is giving the magnitude square of the initial velocity. That means the vx square plus vy square is u square, and which is constant. Okay, good. So we have found the uh, result. We have found the velocities and how the velocities are changing with the time. We have found explicitly. Right? This equation, a very important relation, which is actually resemble to this equation, that is x square plus y square equal to constant square. And this equation is the equation of circle, right? It is telling then that when a particle is entering in a magnetic field perpendicular to it, it will describe a circle. So when this particle is entering here, initially it is entering in here, so it will actually describe a circle in xy plane. And its velocity, the magnitude of its velocity will remain same. That means the speed of the particle is same with u. Thus we have proved that here. So there is no velocity along z-axis. And the force which is acting on the particle is actually pointed towards the center. Hmm? Uh, how can I know that? Because of the expression of the force. It is coming from the expression because F dot B at any instant of time because of the cross product, and we know that we have already decided the force is perpendicular to the both V and B because of the property of the cross product. F dot V is always zero at any moment. That means the when a particle is moving in a circle, we know the velocity V is always tangential, and to this tangent, if the force is acting and it is perpendicular to it, it must be towards the center. Okay, so F dot V is equal to zero. So F is now playing the role of centripetal force in this circular motion. Okay, so you can easily see from this picture that V, F, and B three are now perpendicular to each other. So B along the negative z-axis, F and V and F are lying on xy plane but perpendicular to that. So it is easy to see that V, F, and B are mutual perpendicular. And since V is constant, the speed is constant. It is a uniform circular motion. Yeah. So, so now we are going to analyze the dynamics again. So we have we have found that the F is the centripetal force in this case. The centripetal force and we know that V and B are perpendicular to each other. So the magnitude of F is QVB sine 90 degree. So it becomes QVB. And F, according to the centripetal force formula, F is mv square by the radius of the orbit, circular orbit. So from this expression, we have found the radius of the orbit is mv by qv. That is the linear momentum by qv at any moment of the particle motion. So we have found the radius, and again we can find the angular frequency. Angular frequency is simple v by r. So V by R is the angular frequency, so it becomes QV by N. Simple. And this angular frequency, so angular velocity or angular frequency, okay, can be related to the time period of the particle rotating in the circular orbit. So time period is 2 omega by 2 pi by omega, that is 2 pi m by qb. That is the time period, right? Time period is the time it will take to rotate to rotate the circle once. So that is the time period. Okay. We have found all the things properly. Okay. Next thing is to consider the second case we are now going to consider. So here we have taken the velocity, the initial velocity as u, but it has a component along z-axis. Okay. So it is the second case. So initial case was the when the particle is entering, it has only two components. Now when its initial velocity is considered now, is the u has three components. So ux I cap plus uy j cap plus uz k cap. and the velocity and the magnetic field uh, is same as was taken before. So it is again pointing along negative z axis. But what we are going to do is to apply a trick so that our analysis can be simple, can be simplified. So I can write u as u. So xi. So I have to first draw the um, direction of the magnetic field properly so that what I am going to tell can be made clear to all of you. This is x, this is y, and this is z axis, and b is pointing inward. So this is along the negative z axis, and u has now three components. So xy plane is perpendicular to the negative z axis. So xy plane, so whatever the velocity, whatever the components ux and uy are lying along here, ux and uy, the resultant of ux and uy here say this resultant which is lying in xy plane is perpendicular to the magnetic field. So what I am doing is I'm going to group the I'm going to first the I'm going to find the resultant of ux and uy first, which is lying in xy plane, and writing this as u perpendicular in the sense that u perpendicular is the resultant of ux I cap and uy j cap, and obviously it is perpendicular to magnetic field because it is lying in xy plane. And since uj, that is that is the velocity along the z axis, is aligned opposite to the magnetic field, I am writing is as u parallel. Okay, because it is parallel or anti-parallel to the magnetic field. That's why. So u parallel is uj I cap, uj k cap, and parallel to the magnetic field. Okay. So now our job can be made is here. So at any instant, again the velocity of the charged particle has three components, and that can also be decomposed into two components like what we have done for the initial velocity. So v perpendicular and v parallel. The perpendicular is lying in xy plane, and parallel is lying along the z direction. I think it is now clear to everyone. And we are going to write the force law again. So V cross B, and V can be written as V perpendicular plus V parallel cross B. And we know that the V parallel is parallel to the magnetic field. That means the cross product is zero. So only the cross product is contributed by the V perpendicular. And we are going to write the force into, again, we are going to write now the force. We see that the now force can be written also in terms of parallel, sorry, perpendicular plus parallel components. Good. And that must be equal to V perpendicular plus. Okay. So we can see from this expression that right side, right side is a vector because it is a cross product V and B, V perpendicular and V. That means the right side is a vector is perpendicular to both V and B. V perpendicular and B. Okay, I'm going to tell again. So right side is a vector which is perpendicular to V perpendicular and B. B means parallel to B here. So the right side is both perpendicular to B perpendicular and along B. So we can conclude and please see the left side. Left side are two vectors. So MA, which is perpendicular to the B, and MA parallel, which is parallel to B. But since the right side is not containing any vector which is perpendicular to B, because it is a cross product between the perpendicular and B, then the right side does not have any component. So we can write here the right hand side does not have any component along perpendicular and parallel to B, right? So the right hand side does not contain anything because it is a cross product of the V perpendicular and B, and this cross product is itself perpendicular to the V perpendicular and B. So you have to understand from this equation, the right hand side of this equation does is actually perpendicular to the plane where the velocity and the perpendicular velocity and B are present. That means the right side does not have any component along the perpendicular and parallel direction to the B magnetic field. Where the left side do have the components along the perpendicular and parallel to the B, which says that since there are no parallel and perpendicular components in the right hand side, both are equal to 0. That's all. So these are very, very simple thing we have to find. It is coming directly from the property. So if you have any difficulty in understanding, I'm going to draw this picture again to make you understand. So suppose in this direction it is V perpendicular, this is B say, and the cross product is saying the cross product is telling me this cross product has a direction in which direction we are talking about. So the cross product is along this direction. Okay, perpendicular to the both. So this is perpendicular, this is perpendicular. It is both perpendicular to the V and B. But the the component of the acceleration along this direction, component of the acceleration perpendicular in this direction is sitting in left side. But in right side, this vector, this particular vector f is in this direction. Okay. So if I compare the left side and right side, so right side is now, so I'm going to remove the V perpendicular here so to make you understand. So now it is now clear to you. So left side is now A perpendicular, and so this is the left side, left hand side, and this is the right hand side. So there is no match. So there is a big mismatch between the left hand side and right hand side. Okay. So there is no components we can compare between the left hand side and right hand side. That's why the both are equal to 0. So that's all. That means the if EA perpendicular equal to 0, that means the V perpendicular is constant, and similarly V parallel is also constant. And we can found this the constant again from the initial values. That means the V parallel is initially again this constant is true for any instant. So I have taken at t equal to 0. So V t equal to 0 is U parallel. And we know from this equation, so we have found this equation. We have solved this kind of equation before. So it is telling the V square equal to constant, and similarly V parallel square is also constant. But V parallel square, this constant can be found from the initial value. Again, t equal to 0, the initial value is U parallel. So this must be equal to U parallel square, and this is V U parallel square. Good. Okay. So this give me the circle again. But now the particle has some velocity along the parallel direction of the magnetic field. What does it tell? It is telling that suppose the magnetic field in this direction, and suppose it is z axis and this is x and this is y. So particle the x and y component of the velocity are describing a circle. But since the particle has a velocity along z axis also, the circle cannot be completed because it is moving in this direction with a uniform velocity along z axis, right? So it is moving like this. It will complete the circle. It is trying to complete the circle, but it cannot because it has a velocity along z axis. So it will moving like this. Okay, it is going up, and this kind of path is known as helical path. So we have we have to conclude that whenever the velocity, initial velocity, has component along magnetic field, it will describe a helical path. It will move along helical path. Keeping the direction of B as axis, as is axis. Good. So final conclusion. So when the initial velocity u has components only perpendicular to the magnetic field, but there is no components along the magnetic field that is initially, then it will give me the circle, and the circle is lying perpendicular to the magnetic field. And the second conclusion is when the initial velocity has two components, perpendicular and parallel to the magnetic field, then it will describe a helical path. Okay, okay. One more thing we have to consider, the work done by the magnetic field on the charged particle. So we have found that F dot V is zero because F is a cross product of V and B. F must be perpendicular to the V at any moment. So F dot V in both cases is zero. And F dot V is the rate of change of energy distribution. So that is dW dt is zero. That means W equal to constant. So this constant is taken at for any time. For at any time the work done is constant. So we can take again the initial condition. So at t equal to zero, the work done on the charged particle again zero because F dot U must be equal to zero, right? So that is why the work done is zero. So work done by on the charged particle is zero. That is very important conclusion. And from we know that the work done can be written as the rate of change of kinetic energy of the charged particle, and that is equal to zero. We have found when the particle is moving in this uniform magnetic field. So K is equal to constant. That means the kinetic energy of the charged particle remains constant. Okay. Since we cannot find the potential energy here from this because the work done itself zero, we cannot find the potential energy of the charged particle at any moment. We cannot conclude the total energy of the charged particle is constant or not. That is why the this force, and since the force depends on the velocity, the F is depending on the velocity of the charged particle, which is a function of time here. The F cannot be expressed in the derivative, cannot be expressed by cannot be expressed by a derivative of a potential. That means F is non-conservative force. Okay, okay. So let me end today, and we will move to the latter part, a second part of where we have to analyze these all the things when the charged particle will move undeflected in a electromagnetic field in the sense that electrostatic field and magnetostatic fields are there, but in such a manner that the velocity of the charged particle is undeflected. Okay, so let me end here today. Thank you, students.